Okay. Now see here. Now this is the sync signal. Now this is the rectangular pulse in time domain whose Fourier transform is sync function. Now see here. Now in this sync function, if you see, now we'll calculate the bandwidth. Okay. Now what is the bandwidth? Highest frequency minus lowest frequency, right? Now what is highest frequency? The highest frequency is infinity minus lowest frequency is 0. So bandwidth is infinity. And some of you are writing that lowest frequency is minus infinity. Lowest frequency is minus infinity. Wrong, because practically negative frequencies does not exist. Practically negative frequencies does not exist. Therefore, you don't take the negative side, only the positive side. Okay. So this is the bandwidth. The bandwidth which is equal to highest frequency minus lowest frequency, infinity. Now bandwidth is infinity. Now this is the theoretical bandwidth. Why I am saying this is the theoretical bandwidth? Because bandwidth is infinite, which is very high. Infinite bandwidth means it is not possible practically, right? So that's why I just call it, this is a theoretical bandwidth. So what do you want? I want a practical bandwidth and I want a finite bandwidth, right? But this is the infinite bandwidth and this is the theoretical bandwidth, I call it as. And FL is equal to minus, FL is not equal to minus infinity. You don't take minus infinity because practically negative frequencies does not exist. Okay, that is one point you remember. And one more thing is also I want to identify. Now, so if you consider the total spectrum, a spectrum is nothing but frequency domain. If you consider the total spectrum, and I can get a bandwidth as infinite. So sir, how I can get the practical bandwidth? How I can get the finite bandwidth? Then if you see here, if you find the energy of the signal, first of all I want to find here. See here, if I want to find the energy, because this is a finite duration of the signal is nothing but energy signal, infinite duration of the signal is nothing but a power signal, right? Now if I take a minus infinity x of t whole square dt, therefore which is equal to integral minus t by 2 to plus t by 2, now a square dt. Therefore energy signal which is nothing but a square into t joules, a square into t joules, right? Now you see here, now this is the energy signal. Now this is the frequency domain signal. This is the signal in time domain and this is the signal in frequency domain. Now this is the major lobe. Now in this major lobe, if I find the signal in the major lobe, if I find, now this is nothing but integral in the major lobe minus t by minus 1 by t2 plus 1 by t x of f whole square df. If you find here, this is in the only major lobe I am finding. Now this is nothing but 0.95 a square into t. Is that right or not? Now this is in the major lobe. If you see here, now what is the meaning of this? Is energy in the main lobe. So what we can understand, 95% of energy information in the main lobe, only 5% of energy or information in the minor lobes. So what should we do for finding the practical bandwidth? So I want to eliminate the insignificant components. The insignificant components are the component where it is having a small energy, small information. So I want to eliminate this insignificant component and save the major component. So how to eliminate the insignificant component and how to find the major lobe and a main information component. Okay. Now by using the filters which is used to select the required component, or filters are which is used to select the required frequencies, or which is used to reject the unwanted frequency component. Okay. So this is 95% of energy in the main lobe and only 5% of energy in the minor lobe. So you can eliminate the insignificant components. Okay. So see here. So now we using a filter. Now filter here is using to find the band limiting. So I want to limit the bandwidth. So this insignificant frequency components are eliminated and only the significant low frequency components are saved. So now I use a filter. Now which filter? The low frequency information. This is F, 2F, 3F, 4F, 5F and so on. Therefore the low frequency information is to save. So use the low pass filter. This is the pass band of the low pass filter. This is the stop band. Okay. So generally practically positive side, but symmetricity, therefore I can take the negative side also. So 1 by T low pass filter. Design a low pass filter. Now this is a gain versus frequency characteristics of a low pass filter. Now this low pass filter will allow the low frequency component and reject the unwanted frequencies. Now if you see here, now this is 1 by T, this is minus 1 by T. Now therefore this is nothing but AT, X of F. Now this is the signaling frequency domain, but after limiting, now see here what is the bandwidth. Now this is the practical bandwidth. The practical bandwidth, which is nothing but highest frequency minus lowest frequency, 1 by T minus, don't take minus 1 by T, there is no negative frequencies, only positive frequencies, which is equal to 1 by T Hz. This is the practical bandwidth. Is a finite bandwidth. What is the theoretical bandwidth? Theoretical bandwidth also you can get the theoretical bandwidth, which is infinite minus 0, which is infinite. This is the theoretical bandwidth which we are not used practically. This is the practical bandwidth which we are using. Okay. So this is the way how you are selecting, how you are calculating a time domain signal into frequency domain signal by using Fourier transform. And if any limitations in this particular frequency selection, use the appropriate filters to band limiting the signal. So what you can understand here, the low pass filter is used to band limiting. So here infinite bandwidth is limited. So this is the band limiting signal, is nothing but a signal which is having a limited bandwidth. Okay. So finally what you can understand, now this is a rectangular pulse whose pulse width is capital T and bandwidth is 1 by t, which means that the bandwidth of the rectangular pulse is inversely proportional to pulse width. The bandwidth of the rectangular pulse is inversely proportional to pulse width. Note down first. The bandwidth of the rectangular pulse is inversely proportional to pulse width. Bandwidth of the rectangular pulse is inversely proportional to pulse width. Now T is pulse width. So if a rectangular pulse whose pulse width is capital T and a bandwidth is inversely proportional to pulse width. Now see here, bandwidth of the rectangular pulse is inversely proportional to pulse width. Now if you see here, this is the rectangular pulse whose pulse width is 1 millisecond. Now this is the bandwidth which is pulse width is 1 millisecond, and now bandwidth is inversely proportional to pulse width. 1 millisecond is inversely proportional, therefore this is nothing but 1 kilohertz. Bandwidth which is inversely proportional to pulse width, which is equal to 1 by 1 milli, which is equal to 1 kilohertz. Now similarly, now this is 1 microsecond. This is 1 microsecond. Therefore 1 microsecond inversely proportional to pulse width, therefore 1 megahertz. Now bandwidth which is inversely proportional to pulse width, 1 by 1 microsecond, which is equal to 1 megahertz. Right? Now similarly, now this is an impulse. What is impulse? Impulse is also a rectangular pulse. Impulse is a rectangular pulse whose pulse width is 0. When pulse width is 0, bandwidth is infinite. 1 by 0, bandwidth is infinite. Therefore Fourier transform of rectangular pulse is, Fourier transform of impulse function is 1, you know that. Now this is the Fourier transform of impulse. Bandwidth is infinite. Bandwidth which is inversely proportional to pulse width, 1 by 0, which is equal to infinity. Now this is the Fourier transform of a rectangular pulse. Now this is the rectangular pulse. Impulse is a rectangular pulse only. Impulse is a rectangular pulse whose pulse width is 0. Impulse is a rectangular pulse whose pulse width is 0. Right? Now if the rectangular pulse whose pulse width is 0, now that rectangular pulse is named as a impulse function. Okay. So Now what we can understand here, now this is the way how a signal in time domain is converted into frequency domain, and if any insignificant components are available, now use the filter to band limiting the signal. Thus here the low pass filter I am using to band limiting the signal such that I can get the practical bandwidth. In the same manner, if any signal are coming in our subject, now there you can find the Fourier transform and find the bandwidth. Now is there any insignificant components are available, or is there any scope of getting the maximum bandwidth? Now use the appropriate filter to band limiting the signal. Okay, so this is the concept of Fourier transform. For what purpose we are using this concept? Now this concept we are using only for the purpose of identifying the bandwidth. Okay, because bandwidth which is very important to our subject. Okay, note on this.